Okay, so in here I have an AC source and a DC source that I'm using for biasing the amplifier. Okay. So it says that IS for this transistor is 1 femtoamps and beta is 100. And the question is, there are two parts. Draw the small signal equivalent circuit. And part two is what is the voltage gain. And when I talk about voltage gain, it's only the small signal part, right? So if it is 2 volts DC plus 100 millivolts AC at the output, it's only 100 millivolts. The 2 volt DC is not included, right? What is the voltage gain? So I'm just going to, on purpose, drop the small signal from here because I want you to keep that in mind, that when I talk about voltage gain, when I talk about input resistance or output resistance, or anybody else talks about these parameters, they're only considering the small signal, not large signal, right? So the DC component is out. Okay, so first thing I do here is that maybe I go and figure out what is my IC. We saw that for any small signal analysis you need that. So go and plug in the values for IS and VT in your equation, and I give you the final number. IC becomes 10 milliamps, 10.7 milliamps, if I use IS e to the VBE over VT, right? And in this case, I only keep the DC component in my calculations. So 10.7 milliamps, I go and calculate VC. Which is going to be 4.9 volts. Quick check to see if my device is in active region. So this is the base collector diode, base emitter diode. Base emitter is okay. Base collector, well, about 5 volts at the collector, 0.7 volts at base. So it's a negative voltage drop. BC reverse biased or BC off. I would say reverse biased. So check, right? And BE on. And BC off, check, right? So active is okay. And then from this point onwards, I'm going to deal with the small signal model. So here's the transistor in my circuit. I'm drawing the small signal model. So I said we get rid of the DC sources. First thing I do is that I draw the transistor. So the transistor is replaced with this model. Collector, base, emitter, right? The values are GM V pi. This is V pi, and the value of this resistor is R pi. How do I find them? Well, GM is going to be IC over VT. I know IC. For this device, it's we found it to be 10.7 milliamps. Calculate GM, assuming a 25 millivolt VT. And GM is going to be 0.43 amps per volt. So GM, as you notice, is 1 over resistance. It's current divided by voltage. So the unit, the SI unit for it, amps per volt, is Siemens, right? That's the official SI unit. You see from time to time that, some books try to be cute, and because volt over current is ohms, current over volt, they call it mho. So they basically read ohm from right to left, and this is the signal they use for it, right? I'm going to stick to the SI unit. So, but if you see mho as a unit, so they call it mho, and that's the symbol, that's what they mean. It's basically current over voltage. And then I have that value, come on. And then R pi is beta over GM, which is going to be 234 ohms. Okay, so that's my transistor. Now I attach the rest of the circuits to it. The rest of the circuit, I get rid of the DC sources and only keep AC. Well, emitter is ground, so that's easy. To the base, I have my AC source V in, and the DC voltage source VBE naught, which now I short circuit, and then what I have is just the ground at the other end. Connected to the collector is RC, and at the top of RC I have another DC source VCC that is 6 volts, but now this is connected to ground as well. So this is my circuit, small signal circuit. It's usually, you know, once you know that what you're dealing with and then the DC source at the top has vanished, you just flip RC and put it below this line as well. So because you know RC is connected to ground, you just connect it like this as well. So this is my small signal circuit. And then what is the voltage gain? Well, I have to analyze this circuit. Well, easy. I can see that my intention is to find V out. If I look at this circuit, V out is whatever the voltage drop across this resistor is above ground. So I look at the current through this resistor. The current is GMV pi, right, times RC. So this is IC. But the current is going from ground up, right? If it was going the other way, if it was going from the top of the resistor to ground, you would get a positive voltage at that node. But if the current is flowing backwards, it's going from the ground up the resistor, then your voltage drop over here will be negative, so you get a negative sign in front of this. Good. I have this relationship that shows how V out is related to V pi, but I want to know how V out is related to V in. Look at this circuit. Well, all of this V in drops across all of that V pi. So noticing that V pi in this particular case is equal to V in, then I can see that V out is minus GM RC. So let's keep that in a bracket here, V in. Okay, done, solved. And that's the gain, GMRC. Now, some of you may realize that this is the circuit that we have seen before. This is the circuit that we analyzed at the very beginning. And we found out that yes, there is a voltage gain, and this is how much it was. The question is that, are we seeing the same thing here? Well, let's look. Keep this equation in mind. IC over VT. And let's see what we got here. If I go and expand this and I say GM is IC over VT, but this is DC IC current, right? Times RC with a negative sign in front of it, times V in. We are back to where we were at the very beginning of the lecture. But it doesn't look that we've saved a lot of time by doing the small signal analysis here, but hopefully you will see the value that as soon as I start to add a couple of other transistors here and there, if I take the small signal route, I'm doing a small signal analysis. It's a linear analysis. It's fairly easy. You just write a bunch of KVLs and KCLs and make your system of equations and solve it. If you are going to do the large signal analysis, life can be more complicated, right? And then a lot of those systems of equations you cannot really solve by easily. Computer can do it, but an engineer that is going to do this analysis in the field cannot. And therefore you have to use iterations or approximations, and in most cases time spent on those is not really going to give you a lot more information than what you can do here. Okay? So we got to the same result with the small signal model, and that's expected. And then in your slides, you have an example with a PNP device, and I suggest you to go and solve that on your own. So in that case, you have a PNP transistor, similar circuit, slightly different in terms of one additional resistor. Solve the circuit at DC, take the transistor out, put the small signal model in its place, make the small signal model, and analyze it and see what you get for that circuit. Okay. So with that said, I just want to move on to the next topic here, which is the concept of input and output resistances for a device. So we talked about this briefly in the beginning, that an amplifier, a linear amplifier, because it is not producing a signal for small signal analysis, when you look at it from the input port, you can consider it to be a resistor. And when you look at it from the output port, there is a dependent voltage source plus an output resistance, right? So these two parameters are very important. So you have this circuit here, and let's say the signal goes from the left to right. So you have V in applied here, I in going in. Inside this circuit, you can have all sorts of combinations of components. As long as it is linear, you can go and simplify all of that to just one resistor. And then at the output, again, you can go and simplify all the stuff with the input signal attached to a voltage source and a resistor. And then the question is, so this is what I see when I look back. I see R out. When I look in, I see R in terms of the resistance, right? The small signal resistance. If you connect the ohm meter there, you don't see that. And just convince yourself that you are not supposed to see, let's say if I tell you that the input resistance of this amplifier is 10 kilo ohms, and you put a multimeter there, you will not measure 10 kilo ohms. You should not. If you measure it, it's just a mistake, it's just a chance. Convince yourselves that you cannot measure that resistance with an ohm meter. Now that you cannot measure it with an ohm meter, we have to find alternative ways to estimate it, and you do that in the lab. But in terms of theory, how do you calculate these input and output resistances? Well, you go and take your circuit, make the small signal model. It must be small signal. Make the small signal model there, and then the issue is very easy. The input resistance R in is the equivalent input Thevenin resistor. The output resistance R out is the equivalent Thevenin resistance at that port. So this is V out and I out, right? So R in, if you want to calculate it, so what you do is what you normally did for a Thevenin circuit. You, step one, remove all independent sources. And this is small signal, so you definitely do not have any DC sources left at this stage. What you're removing now is the independent AC sources. Then well, how did we calculate the Thevenin equivalent circuit? You had one technique from MSE 250 that you calculated the open voltage, open circuit voltage and short circuit currents, divided them by each other. We said that's okay, but another method that we used is that you attached a test source to the circuit. It could be a voltage or current source. If you're using a voltage source, you measure, find, I'm going to say the current drawn from the source. And this is for the test case that you use a test voltage source. I'm going to be a bit more specific. But what I'm saying here is also true if you use a test current source. So you attach a test current source and you measure the voltage that is produced at the input of that port, or you attach a test voltage source and you measure the current, and then R in is V test divided by I test. All of that small signal, okay? So that's how you calculate the input resistance. You calculate the output resistance the same way. But in this case, you again remove all the independent sources. You may have a test source or a signal source here, for example, right? You get rid of that signal source, replace it by a short circuit, for example, and attach your test source to the output port of the device, the circuit, and calculate the current drawn from it. And that gives you R out. So R out is calculated in a similar way. And these values of R in and R out are very important because they help us make that simple model that we had for the amplifier, right? So we wanted to reduce the amplifier to just three components: a dependent voltage source, an output resistance, and an input resistance. If you can do the small signal analysis, and all of them are small signal quantities, then you can replace a complicated transistor circuit with just these three components. And if you're putting these amplifiers in series, in parallel, whatever you're doing with them, now you're only going to deal with a much simpler circuit. So that's what I call input-output resistance of a circuit.